Well, thank you very much for making it to this talk. And this is probably the first one in the last so many months. I'll talk about shale resource characterization. And I'm sure you're all working in shale plays or something associated with that. Now, I'll just begin with the elements that we talk about for a successful shale resource play. And the different elements, they can be listed like this as I have here. The mineralogy, because we need to know the content of clay, calcite, and quartz in the shale, because that has a bearing on the brittleness of the formation. Then we also need information about the organic richness, that is the total organic content of the shale. The maturation, because that again has a bearing on whether it's going to be a gas-bearing shale or it's going to have some oil content or condensate or what. Then the thickness of the formation, the porosity, permeability is of interest. Then brittleness, and of course you guys, you're going to calculate the oil and gas in place before you go ahead with any kind of drilling campaign. And finally, we also would like to get information about the pore pressure, if that is possible. So with this in mind, as I say here, all these, they have a bearing on the productivity. So we would like to get as much information as possible, not necessarily from the seismic, but from other sources. And all that information can be integrated together when you carry out your interpretation. Now, we will touch upon some of these aspects, not necessarily all of them in this 45-minute talk, but let's begin with this TOC content, the total organic carbon content. Now, one of the earliest papers that was published was by Passey in 1990. It's AAPG reference, AAPG bulletin reference. And what he had shown was that on the basis of dozens of shale formations worldwide, the total porosity and the gas content can be directly associated with the TOC of the rock. And so that's an empirical relationship that he published at the time. And in 1990, of course, not many people were looking at shale plays as they are doing now. And so this method essentially uses the log curves, the resistivity of the sonic log curves, and by overlaying these, the scale, the sonic, and the sonic transit time curve on the resistivity curve, you can make them overlay in such a way that they line up in places where you don't have any organic content, but they will cross over where you have some kind of TOC content. So water-saturated organic lean rocks, they will show almost parallel curves, but they will deviate when you have the organic content there. Now for most case studies that have been published, we see that this method is by far the most common method that they use, at least from the log control. Now what we've done is we've tried to implement this particular approach. That means derive the TOC content from seismic data. So I'll touch upon that as we go along. So this is an example directly from his paper. It's not exactly Passey alone. I mean, there are some co-authors also. And as you see here, you have the sonic and the resistivity curves, and the crossover is seen in this zone where we have this the TOC content. And what also they have shown is the TOC calculated based on the empirical relationship that he published, that is shown correlated with the core information that they have. Because TOC can also be calculated, or it can be determined with the geochemical analysis, etc. So that information is shown here in the form of these dots from the individual core samples. And as you see, it matches it pretty well. So we can apply this this methodology as we go along. I'll show you. But we tried to apply this, way back in was it 4 or 5 years ago when we started looking at the Horn River Basin, the data from Horn River Basin, and where we have the Muscova Shale, and then we have the EV, Autopark and the EV formations also. And we had something like this, where we have the resistivity log in red, and the blue is the sonic transit time, and it does cross over in the EV shale unit. And so it did show results that we were expecting. Now, the shales found in different basins, they are found to be, they're going to be different because that's how the formations are laid in different settings, and so their the TOC content is going to be different. Now, not only the TOC content, if you look at this this chart here, we have matrix permeability, thickness, and producible gas, and the gas in place, and all these different properties that have been determined for different shales. As you see here, the Barnett, Haynesville, Marcellus, Horn River, Eagleford, they all have a variation. And it's not only these properties, we can have a look at the depth at which the individual shales are prospective. As you see here, Horn River Basin is deeper, and so is the Eagleford and the Haynesville. Besides this, the other properties of interest are the TOC, the porosity, because we are talking about shale plays, and the porosity and permeability that is going to be low, unlike the conventional plays. And the witrinite reflectance, RO, that is also varying. So many of these properties, obviously we cannot determine all of them from seismic, but some of these properties we can determine. Besides this, the pressure also plays a role, because the pressure, the more the pressure, the more production is going to take place. This slide or image I picked up from reference here, I put down, and this from the Marcellus Shale. What they show here is that the west side has a higher TOC content and is shallower. The east side is deeper and thicker, and it has higher quartz content. And the northern side is overpressure, the southern side is under pressure. And also there are fractures in the southern part, and whether they are fractures in the northern part or not, that is questionable. So the point is that these properties, they vary spatially. Now to determine, because all these properties that I mentioned, we have a good feel for this at the well location of the wells, but we would like to know how they vary spatially, and for that, what could be better than employing the seismic data. So the thickness, the fracture permeability, organic richness, brittleness, pore pressure, they can be determined. At least we try and determine these properties and correlate that with the available log control, and then try and see how well we've done the job. Thickness, that is straightforward, because from seismic data we can determine the isochrons and then determine the isopacks, and so that is a no-brainer, that's fine. The fracture permeability, if there are natural fractures in the shale formations, we can determine this from, or shall I say, by the application of coherence and curvature type of attributes. But the point or the problem that we normally face is that many times the frequency content of the seismic data is not good enough to give you that kind of discontinuity detail. If you have your bandwidth going up to something like 70, 60, 70, 80 hertz, and you want to determine fractures, large fractures, you're not going to be able to see anything. So that is something that you have to keep in mind when you're going ahead with the application of these kinds of attributes. So a workflow that you can possibly think of is, okay, we have the stack data, stack migrated final data that you are interpreting on your workstation. You can determine coherence and curvature attributes. Obviously, I'm not going to go into the details of how we do this, and because I think I've been talking about that for the last so many years. You have to precondition your data, you have to make sure you have the proper bandwidth, and you have to have the proper type of algorithms, you have to have the dip steering option switched on, and things like that. So we'll just take it for granted you are aware of all those kinds of things. So coherence and curvature, they are really good attributes, especially if you use the algorithms like the eigen decomposition type of coherence algorithms. And once you've done that, then the next step is to be able to correlate that with the available log control. And the log control that I'm referring to here is the image logs, for example. The image logs, they give you the orientation and the intensity of the fractures. So we can generate those Rose diagrams on the coherence or curvature displays, especially if you have enhanced your images with an application like the AND tracker in Petrel. So it does a good job. So if you have done that and you can pick up those fine lineaments, you can generate a Rose diagram at the location of the well or around it, and then correlate that with the image logs, and that should give you some kind of confidence, depending on how well it matches. And so that is one workflow that will help you do that. Here I'm just showing you what I'm sure you've seen all this. This is from the Horn River Basin. This is the most positive curvature that I'm showing you. And the big ones are probably the faults that we have in that area. And the finer ones, the smaller ones, they can be associated with fractures. So this is one such plot, but then the way we use it is, like for example, if we have generated a relative acoustic impedance attribute from the seismic data, we can overlay these two and see how good or bad the correlation is, where they exactly fall on the lineaments fall on these different pockets. Like in this particular case, we have I don't have the color bar, but the low values of impedance, they are in blue, and the higher impedance values are in the hotter colors. So this kind of an exercise you can carry out. And another thing that we have been doing in the last little while is we generate these Rose diagrams automatically from the seismic attributes. And to determine this, we make use of an attribute that we refer to as the azimuth of minimum curvature. That is one attribute we can calculate for our seismic data. And the other one is a shape attribute, which could be something like a ridge attribute or a channel type of an attribute that we can calculate. So from this, we determine the intensity of the lineaments, and the orientation comes from the azimuth of minimum curvature. And at every interval, with this bin that you see here, this is not every bin in the seismic data, but we choose an interval like something like 500 meters by 500 meters or 1 kilometer by 1 kilometer, and determine these or generate all these Rose diagrams in every such bin. And as you see here, this is from the Woodford shale. You see these kinds of pockets which have a different orientation from the other orientations that you see on this display. So this is doable. This is not biased by any kind of interpretation. No interpretation goes into generating this except the horizon that has been picked up along which we are showing this. So this is determined over a volume, and then you can display it along the horizon of your interest. So you have the most positive curvature, most negative curvature, and this is the Rose diagram attribute that we have calculated. So this is possible now, and then we can have all these different orientations from the AND tracker, like I just mentioned. They can be overlaid on the impedance, acoustic impedance plot. This is again from the Woodford shale, and a composite display like this, or a composite volume can be generated, which you can carry out your interpretation on. So this is just the discontinuity part. So let's move on to the other attributes, which are more to do with the TOC application. Now, okay, there is still one more, because some interpreters, they have a liking for azimuthal AVO, because that gives you the orientation and the intensity of the faults and fractures. So you can make use of this. It's a pre-stack process, and sometimes it works well, at other times may not. I'm not sure what your experience is for this particular application, but the way I look at it is, because it's a pre-stack process, we should get more information out of azimuthal AVO, and we should be able to correlate that with the post-stack attributes, and then do an integrated type of interpretation. In the application that I've seen, it works very well for limestone formations, where you have the faults and fractures. But for sandstone formations, I'm not sure. But that is again my personal outlook. It is up to the interpreter to decide how much information you can get from there and go about doing that. Now talking about brittleness and TOC, we will indulge in simultaneous inversion. And if you have multi-component data, then we will talk about joint inversion also, post-stack, pre-stack. Now here I've just put down pre-stack seismic data, because with post-stack seismic data, all we are going to get is acoustic impedance. And with pre-stack, we are going to get the P impedance, the shear impedance, and we can make use of both these to determine properties like lambda rho and Mu-rho, Young's modulus, and many other attributes. There's another one that I'll talk about in a moment, a new attribute. I'm not sure if you've heard of that, but we find a lot of value in using that, especially for data sets where we don't have long offsets and we cannot determine density attribute. So this is simple now. Lambda rho, Mu-rho you can determine, and instead of lambda rho, you might want to determine K-rho, where K is the bulk modulus. And again, they are very similar, and that is why lambda is also considered a proxy for bulk modulus, or the incompressibility of the rock formation. So the way it goes the workflow goes is, you have the pre-stack data, you are going to condition it and then run your simultaneous inversion. And then the attributes you get are the P impedance, S impedance, and density when you have data with very long offsets or large angles. So that helps you determine VPVS or Poisson's ratio or Young's modulus. And Poisson's ratio is a measure of the strength of the rock. The Young's modulus is a measure of the stiffness of the rock. And of course, we can make use of both these attributes. High Young's modulus and low Poisson's ratio should be a measure of brittleness. But then you cannot just take it for granted that this will work in every case. Like for example, I like this particular case study that was published a couple of years ago by Progress Energy, Mark Norton and others. And what they show here is a vertical section from the Poisson's ratio attribute that they determined. And this is how it correlates with the logs, the inverted and the measured Poisson's ratio correlation is shown here. Here is a display along the horizon at the level of interest, and this is the untracked volume that you see here. The horizontal wells you can see there. Now what they've done is they have acquired this microseismic data, and when they overlay the microseismic data, you see that this is the area which has the high values of Poisson's ratio in blue and purple, and the low values of Poisson's ratio are all in these hot colors. So notice now all this fracking that they see here is all in the zone or zones where, or especially it is in that place where you have the low values of Poisson's ratio. So this application is quite convincing. And of course here, you can pick up a small place here or there, but overall it follows the low Poisson's ratio values. Now, Poisson's ratio we can easily determine from IP and IS. And what we've come up with a couple of years ago was another attribute that we call as E-rho. Not E is the Young's modulus, which is a measure of the stiffness of the rock. And to determine E, we need the density. So if you have data with very long offsets, large angles, you can determine density, and then of course you can determine Young's modulus. But then normally for normal data acquisitions, we don't go with very long offsets. So we found that this E-rho attribute, it can substitute for those data sets where we don't have long offsets. It's just like Mu-rho, a scaled version of Mu-rho. So I'll come to that in a moment. But again, the workflow is still the same. The simultaneous inversion can give us all this information. Then organic richness. Now for organic richness, we would like to see the density attribute as one application. So again, density for long offsets we can get here, but we will look at other methodologies that we can make use of. Like for example, here is one methodology. This is again from a recent paper that we found in the literature. That is based on the core samples and the rock cutting samples. They have determined the acoustic impedance. This is measured, and this is the organic content determined from the geochemical analysis. And this particular plot is for the Kimmeridge Shale in southern England, and it's at the depth of 1,500 meters. And this one is from the Heckingen Formation, the Barents Sea. And again, you notice total organic content, and as a function of this, acoustic impedance shows a nonlinear relationship. Now, if you are able to determine this, you can determine acoustic impedance from the seismic data using post-stack or pre-stack simultaneous inversion, and then use this relationship to transform that into a TOC volume. And that is what they showed. Now, in this particular case, they have data from different wells, 12 wells from the Norwegian Sea, and those zones that you see in hot colors, they are the ones that are showing you that correlate with the high TOC. Here is the amplitude section, and this is the near section, this is the far section, and this is the top of the source rock, this is the base of the source rock, and you see how the signature changes. Now, there are some cases where you can carry out E-rho analysis also. The top of the source rock, what type of signature does it give you? The base of the source rock, what type of signature you can expect there? So in this particular case, they found that the top one was giving a class 4 type of an E-rho response, and the lower one a class 1 type of an E-rho response. But that does not mean that this is going to hold good for every shale plate. It changes, and that is dependent on what type of content you have in the formation. Now, here is what they had done, and this particular methodology is very convincing. Here is your seismic section, and this is the zone we are looking at, the shale zone. This is your acoustic impedance, and as you see, the acoustic impedance varies, and it is lower on the upper part, and it becomes somewhat. It increases somewhat in the lower portion. And then using that particular relationship, you transform that into a TOC volume, and that is what probably you would like to get a TOC volume from your shale formation. As you see here, TOC percentage varies from 3 to 10%, and there is a 10% thing here, a 10% zone, the very shallow zone, has a very high TOC. Of course, what is the range of values, TOC values that we normally expect? Anywhere from 2% onwards, and usually it goes from 2 to 3, 4%, 5%. We are very happy with that. But in this particular case, it goes way beyond. So now let's talk about the E-rho attribute on Montney shale. This is how we started off. This is the Mu-rho attribute. I apologize for this light green color. This was, how should I put it? The guy who works with me, he didn't realize that this will eventually be projected on the screen. So he just used that color, light green. But that is the Mu-rho curve calculated from the IPIS curves. And this is the E-rho curve that has again been calculated. And again, the formula for E-rho is here. You can manipulate the formula for E, which is given here. But even before this, E is given as in terms of bulk modulus also and Poisson's ratio. And so you can substitute the values and arrive at these formula. But notice this, how emphasized the variation is for the different litho units as compared with the Mu-rho. And that is important. The variation that you may not see on the Mu-rho attribute, you will be able to see that nice and clear on the E-rho attribute. And that helps in our interpretation. This is one aspect. The other one is the thing that I mentioned about the density part. I will show in a moment how the E-rho, it varies exactly like the Young's modulus. But the reason I say that E-rho is a scaled version of Mu-rho is, you look at this formula, this is E, and then you look at just multiply by rho on both sides, you get IS squared is Mu-rho. And so you know that E-rho is Mu-rho times this factor. And if you substitute Vp by Vs equal to 2, you get E-rho equal to 8 by 3 times Mu-rho. So it's a scalar. Similarly, if you have a gas sand, the VPVS is 1.5, E-rho is again 11/5 times mu-rho. So again, it's a scale. So you can substitute any value for VPVS, it is going to come up like that. Here is the curve for E derived from these three curves, and the E-rho derived from this, again, these three curves, you need IP and IS. Notice the similarity between these two curves. Are they the same, or they are similar everywhere or not? Well, we can check that. We don't have to depend on our eyes all the time. Check that. So you cross correlate the two curves at zero lag as a maximum correlation. So that tells us, yes, they are very similar. Similarly, you pick up another one. Again, E and E-rho curves, they're very similar, and again you can do this. So these things, they don't take much time. You can quickly go through this exercise. So, but the implication is important. Here is the E axis. This is Poisson's ratio. And for brittleness, I am going to depend on low values of Poisson's ratio and high values of Young's modulus. Now look at the same cross plot, but with E-rho and not E. As I go back and forth, you can see that the overall pattern is not different. But the E-rho, it shows a little opening up of the cluster points. Right? All right. Now you can pick up these points just at random, or if you have some preference for picking up a cluster here or whatever, you can pick them up here on E-rho, E-rho versus Poisson's ratio, or the E versus Poisson's ratio, and back project them. As you see here, Poisson's ratio and E curves are given. Back project, they are highlighting almost similar zones. All right, so this is all good. And again, this workflow is nothing different. It's just the simultaneous inversion. You compute E-rho and you're done. So from seismic data now. Now this is a test we carried out. And again, this work was done about 3 or 4 years ago, just to convince ourselves that if we determine E-rho from seismic data, then it should be the same as the E which we can determine from it, if we have long offsets. And this particular data set had angles up to 49 degrees or so. So we could determine the density attribute for angles beyond 40 degrees. As you notice here, I've overlaid the angle information on the NMO corrected gathers. And notice here we can go in this zone, we can go up to the cyan color, that is about 49 degrees or so here. So using this, I can compute Young's modulus. I can also compute E-rho. So here is your first look at the Mu-rho section, and this is the Montney zone that I show here. Above this is the Nordegg and the Fernie, and the comparison of this with the equivalent E-rho section is this. Notice how compact the zone looks here as compared with this one. The interpretation that you carry out on the E-rho is going to be more accurate than the interpretation that you carry out with just the mu. And that will become clear as I go along. I show you some applications. Here is one horizon slice that I show you from the Mu-rho volume, and this is the equivalent slice from the E-rho volume. Some of the variation is more obvious than just a monotonous section that you see here. All right. Now, because I have long offsets or large angles, I can determine the density attribute. And this is the density attribute section from the density volume. And this is the density curve that you see here. The upper Montney zone is up here. The lower Montney, as you see here, below that. Now, the two curves that you have, the inverted in blue and the measured density in red, they are shown here. And you see for yourself how good or bad the correlation is. One is coming from the seismic data, the other one is measured in the well. This correlation is not bad. Considering the measured curve comes from one point and the seismic data is spread over hundreds of meters, several tens of meters to to a few hundreds of meters. It's an averaged effect, but still the correlation is good. Now, this is the time slice from a 10 millisecond zone within the Montney from the Young's modulus. Because I have the NC, I can compute Young's modulus only. And the equivalent display for the E-rho, you notice now. If you notice carefully, you'll see some minor changes, but otherwise the overall variation is similar. So this is Young's modulus, and this is your E-rho. So what I'm telling you here is that if you don't have very long offsets, you can still get away by determining E-rho in place of just E. And that is a very good application. Yes?
You do an experiment where you chop the offsets to do a similar experiment.
Well, we could do that now that you suggest, but it never occurred to me. All right. So then, of course, we do a lot of this cross-plotting when we are trying to evaluate, these attributes and focus on our narrow zones of interest. So here is the E attribute on the vertical axis and the Poisson's ratio on the horizontal axis. And notice now this is a little different because that's how the arrow indicates. Normally we have the arrow in the upward direction. But what we see here is for low values of Poisson's ratio and high values of brittleness, this will be the cluster of points that will be interesting. So the brittleness increases in this direction on this one. The E-rho has a similar type of a variation, and notice here. And when I go and put a polygon here and here, this is just for comparison. This is from the E versus Poisson's ratio. This is E-rho versus Poisson's ratio. I back project these onto the vertical. Notice this is the points coming from E versus the Poisson's ratio, and this is from E-rho versus Poisson's ratio. Very similar. In my zone of interest, this the red part that is getting highlighted, that is very similar. Now, sometimes, of course, here in Calgary, we don't do that quite often because Bill Goodway introduced lambda-rho and mu-rho to us, and so we've been following lambda-rho and mu-rho. But at other places or in the literature, you will see that instead of lambda-rho, people like to determine bulk modulus times rho. They call it K-rho. So, because we found it in the literature, so we thought, well, let's be a little different. So this is K-rho versus mu-rho, and this is what we get for zone of interest that we captured there, that covers the Fernie, Nordic, and the Montney formations. Now, if you determine a similar or generate a similar cross plot for the same zone, but with E-rho versus K-rho, you see how it opens up. The cluster of points that they separate out, and now you can put or you can highlight these points with these polygons, and they will give you a much better response. How? This is the back projection picked up on this one, because the points are overlapping. You cannot do a good job in picking separate polygons for individual points, and this one opens out much better, and so from here we go here. And this is, you are able to pick up narrow zones in your zone of interest with this rather than with the mu-rho. And that is something I started off by saying, yes, it gives me finer variation on the log curves. So this is a useful attribute. So far, what have I said? We have proposed a new attribute in the form of this product of E and rho. Using well data, I've shown that there is a similarity between E and E-rho. And the cross plot also provides the same information in the form of brittleness. And the clusters in this K-rho, E-rho space, they corresponding to the lithofluids, they seem to be, they discriminate the lithology much better. So much for this bit. Now let's go to the methodology for thin zones. Sometimes, we have Duvernay, which is thick zone, 44 meters or so. I have an application I'll show you. And in that, the main zone, where you want to focus, which is more productive, that is only 17 meters. 17 meters from your seismic data. Are you going to see something? But we will have a look. So, this guy, Rickman and his co-authors in 2008, this was a paper published in the SPE, Petroleum Engineers paper. They showed that pre-stack seismic data with simultaneous inversion can give you this. And since then, we've been following this. Now, this one, if the bandwidth of the data is not good enough, this is not going to give you the kind of detail that you're looking for thin zones. But what we've done is we've modified this workflow. Instead of using simultaneous inversion, what we do is we go ahead with the Fatty's approximation to the Zoprit's equations, which we used to do earlier. And the reason is that pre-stack data to, or shall I say, to boost up the frequency content of the pre-stack data is not an easy job. You can run spectral whitening and then, you can feel happy, yes, you boosted up the frequency content, but then you distort all your amplitudes, and that are diagnostic of many of the parameters that we are trying to determine. But with this post-stack process that we have here, we first determine the RP, RS, and the density attribute. Again, you see that asterisk there, and it is again dependent on the offset information and the quality of the data. So if we are able to determine these attributes, we can run thin bed reflectivity inversion, and once we've done that, we filter it back to a higher bandwidth than the input seismic, or the input attributes. In other words, suppose my bandwidth of the data for RP and RS is 10 to 70 hertz. I can get a data set which has a bandwidth of 10 to 110 hertz, 100 hertz, 120 hertz, something like that. The reason I'm not giving you any high-end frequency is that it is all data dependent. And you will have to convince yourself that whatever you get after filtering the data back to a higher bandwidth than the input, that correlates with all the available wells in the area, even though you don't use any well control for running this process. So that should be a good consolation. No well control is used for running this thin bed reflectivity inversion. So once I have this volume, I will run model-based inversion on that, generate IP, IS, and then I'll be able to determine my properties, Young's modulus or Poisson's ratio or lambda rho, Mu-rho, whatever. So here is a cross plot that I show. This is P impedance and the S impedance. And with lambda rho and Mu-rho cross plot, I see some of these points, they tend to, these cluster points, they tend to open up. And VP by VS with the P impedance, it shows me this kind of a thing. But this is all from log data. So when I back project those points on my on the vertical log control, I see that many of these zones where I have the high TOC, this is that Passey's approach again, the crossover between the sonic and the resistivity, they are highlighted. Of course, I must have picked up some other points around it. That's why you see a little bit here and a little bit there. This is your input seismic, the lambda rho section using the Rickman's workflow. And this is the section that we get once we've done this enhancement of the frequency and then go about doing our job. So there is merit in deriving something like this and then doing your interpretation in terms of lambda rho and Mu-rho. Now you have this using the Rickman's workflow, and this is using this new approach, this enhanced data. And notice you don't have, you have a better separation of these points here. That is what you would probably like to pick up. Low lambda rho and high, usually it is moderate to high values, not very high values, because we are not talking about just the gas here. And when you back project these points on the vertical seismic, it highlights this on the Rickman's workflow, and it gives you something like this on the new workflow. So there is more information, detailed information that you can pick up here. And again, if I have something like this, E and sigma, that is Poisson's ratio, you can pick up this polygon here, and back project that, again, you have something very similar in the same zone. Now this is coming from the upper Montney formation that we are looking at here. And if you generate your horizon slices, they are going to show you this kind of variation. This is on the Young's modulus, this is on the Poisson's ratio, high Young's modulus, low Poisson's ratio, and that's how you pick up your sweet spots, as people like to call them. So this was this small bit about determining or enhancing the bandwidth of your data before you run these kinds of attributes. Here's another one from the Montney shale methodology where we used extended elastic impedance. I'm sure you're all familiar with the extended elastic impedance. Elastic impedance is angle dependent impedance because the normal acoustic impedance is only at a zero offset trace. But when you extend that to angle dependent, we talk about elastic impedance, and then you can extend that further, and that is what we refer to as extended elastic impedance. So I'll come to that in a moment. But again, here the properties of interest are porosity, the organic richness, the high gamma ray, because that's going to be diagnostic of the shales, and of course TOC has a relationship with the uranium content in the shale, and then brittleness is important because it makes the rock fracture better. Now, in the upper Montney, we will look at the log data, and when we do that, we find that it has high porosity, it has moderate gamma ray, it has a high delta log R, and delta log R is the crossover between, that is the Passey's approach. High brittleness coefficient, and I haven't introduced brittleness coefficient, I'll come to that in a moment, and low Poisson's ratio. So, the workflow that we followed was like this. We want to determine porosity, we want to determine gamma ray, but gamma ray from seismic is not an easy job. You don't do that so easily. Because if you do any type of cross-plotting between gamma ray and say P impedance or S impedance, you'll find that there's a huge scatter. There is no straightforward relationship. So it doesn't work like we use porosity and acoustic impedance, it works at times. But gamma ray doesn't work like that. So we went to extended elastic impedance. Passey's method we determined because we could determine delta log R from there. And then simultaneous inversion gave us E and Poisson's ratio. And so that way we were able to determine all these different properties. Now instead of going through this workflow, I'll show you what this extended elastic impedance entails. But again, notice this is the zone that we wanted to characterize, this upper Montney formation. And the porosity and the gamma ray of the Montney shale, if you look at the log control, Poisson's ratio as a function of E, this is the upper Montney. Notice it does not have high values of Young's modulus. We have been saying high Young's modulus, low Poisson's ratio is diagnostic of brittleness. But it doesn't follow that procedure here. So it has to be a case-by-case thing. You cannot just take it for granted that that will work everywhere. And when you back project, you know that this is coming from the upper Montney zone, this is the lower Montney, so it's all good. You see, when you land up in a situation like this where you know that the normal or the conventional methodology doesn't work, you can get into something like this, because this is a brittleness coefficient definition that was given by Mullen. And what he talks about is that let's determine brittleness coefficient from the Young's modulus and the brittleness coefficient from the Poisson's ratio, and then average the two. And people use this. Because now you are not going to land up in a situation like the one I showed you here, low values of Young's modulus. So when you adopt this kind of a thing, the brittleness coefficient still gives you higher values as a function of Poisson's ratio on the cross plot. So you have to find a way to go forward. So here, this set of points that you see in the cluster, they are coming from the upper Montney zone, and that is what that is of our interest. So this is the equation that Passey had introduced, delta log R, and that is this baseline that you take here, where you have the overlap, and the no overlap part comes as delta log R. So this is the transit time here, the baseline, and this is the other values outside the baseline. And so you can determine delta log R from the log control. To determine a property from delta log R, you need to determine what attribute has a relationship with delta log R. So we try out different attributes like VPVS. We can determine this from the seismic data. If we do impedance inversion, simultaneous, we get IP and IS, we divide the two, we get VP by VS. And if I know a relationship between delta log R and VP by VS, I can transform my VP by VS volume into delta log R volume. But here, look at the scatter of points around this. This is from the log data. So we are not going to use this. We tried Poisson's impedance, and again, there is a huge scatter of points. Lambda by mu doesn't work again, but lambda rho works. It does give us a relationship which is almost linear. And we have a best fit line giving us a 92% correlation. So we make use of this relationship. We determine lambda rho volume from the seismic data using simultaneous inversion, and then we transform that using this relationship into a delta log R volume. Now, from the log data, using this relationship, you see the computed curve using the relationship that I showed in the previous slide, and the actual delta log R curve. Notice how good the match is. Because that is something you have to do as a QC to convince yourself it works. Not at just one well, for all the wells that you have in the area. And when you have something like this, then you can go forward. Now, coming to extended elastic impedance, you are familiar with the two-term E-rho equation, the Aki-Richards approximation, and it has an expression like this: R theta or R is equal to A plus B sine squared theta. Now, in extended elastic impedance, as was introduced by Whitcomb and others from BP, they had transformed this, and instead of the angle of incidence, theta, they made a change of variable, and the sine theta they substitute with tangent of this angle chi, and they transform the whole equation as what they call extended elastic impedance as a function of chi, so that for the normal data that we see, this is the range of angles that we come up with, because our offsets are usually like this. With this new methodology, the range of values over which this sine squared theta will become physically defined, that is this range. And so this is the equation here that I see, that I show you: acoustic impedance and what we call gradient impedance. Acoustic impedance is simply your normal at almost the intercept that you have. Gradient impedance is more like the slope that you have in the intercept and the slope domains. So if your chi angle is 0, you get acoustic impedance. If your chi angle is 90 degrees, because the angles of chi, the range of angles of chi, they are not 0 to 30 degrees or so. They now vary from minus 90 degrees to plus 90 degrees. Because of the change of variable, sine theta is now tangent chi. So when you do that, the range of values they increase, and that is what I'm showing you here. Not only this, but we'll be able to see a lot more from minus 90 degrees to plus 90 degrees. Now, using this formula, what they do is they calculate the extended elastic impedance at all the angles between minus 90 to plus 90, and that'll give you these type of curves. Now, you correlate each of these curves with the individual property that you want to determine. Like for example here, lambda curve determined from the log data. If you correlate this with this extended elastic impedance curves generated at every angle, at 19 degrees you see there is a correlation coefficient of 0.99. So what it means is that extended elastic impedance at the angle of 19 degrees is your lambda curve. And the beauty is that here lambda you can determine from the log data, extended elastic impedance 19 degrees you can determine from seismic data. But you need to know the angle for a particular property. And that is what you can do here. Like these are 4 different curves, and this is the range of angles minus 90 to plus 90. This is your correlation coefficient. for 4 different wells, and notice they all show a correlation, negative correlation at an angle of 18 degrees. These curves, they are all increasing, so we cannot go to the maximum. So we restrict ourselves to only to this angle, which is 18 degrees. But should you have a property like water saturation, you will see that they go up to on the positive side. Like gamma ray, for example, this is only the porosity curves I'm showing you here for well 1 and well 2. Extended elastic impedance curve in blue, and the porosity curve is the measured curve. You notice the similarity between the two. Similarly, this is the porosity and the extended elastic impedance at 18 degrees, and similarly we got curves for gamma ray at 38 angle chi. So now with these two angles determined, we can determine the porosity and the gamma ray from the seismic data. So this is again the workflow. I don't have to go into the details. This is for simultaneous inversion. You have to condition your data, do the angle gathers, angle stacks, and so on, and then go through the inversion analysis and do your simultaneous inversion. This is your lambda rho section from the simultaneous inversion, and this is again just one section, representative section I'm showing you, but this volume is transformed into delta log R volume. So delta log R volume as a function of porosity, I'm showing you here. This is from the relationship derived from the lambda rho volume. This is the porosity, and I expect high porosity for my zone of interest, a high delta log R value, and this is what I will pick up. When you back project it, this is the zone. You know these points or these portions of the section, they are prospective in terms of this relationship. Similarly, when I have brittleness coefficient as a function of Poisson's ratio, I back project it. Again, they are very similar. Not exactly the same, but because your brittleness coefficient may not be high at every point where you have this the brittleness coefficient, and this earlier one was the delta log R. They may not be the same at every point. So delta log R volume means high TOC, and then at places where they are brittle, you have to have the high brittleness coefficient. So this can be carried out, and then wherever the two overlap, those are your sweet spots. Does that make sense? Or I just keep saying. I know there is a lot of information there, but this methodology works very well, provided the data is reasonable, of reasonable quality. And then, of course, you can determine horizon slices in your zone of interest. We are talking about the upper Montney. So upper Montney, just below the top marker, we go 10 milliseconds, 15 milliseconds, and we see only these small points. As we go below another 15 milliseconds, it starts highlighting these points. Another 15 milliseconds gives you this, and another 15 milliseconds gives you this. So you know what the thickness of that zone is, where you can focus. And then, of course, So in this methodology, what have we talked about? 91% correlation between delta log R and lambda rho. And we use angles of chi 38 and 18 degrees for gamma ray and porosity. Determined those attributes from seismic data. And observed that high Young's modulus and low Poisson's ratio is not working here. So we go to the brittleness coefficients and then adopt that cross plotting to go ahead. So this was this bit. Then I have a Duvernay case study. Anybody working in Duvernay here? Well, keep your eyes and ears open then. Here's more. You see, the Passey's method, when he talks about delta log R, the delta log R from Passey's method, it can be converted into TOC with this equation. This is from Passey's paper. So you see here delta log R times this factor. And this factor also has this LOM, that's the level of maturity. So if you know the level of maturity, you can compute TOC. Now this is normally not known. They find that through geochemical analysis or something like that. And when the projects come to us, usually that information is not given to us. Either they don't have or they don't want to provide, whatever the reason. I don't think the latter is true, but former is definitely true. So The LOM, what we found was the LOM as a function of delta log R. If you use LOM as 7 and 8 and 9 and 10 and all the way to 14, you see there is a linear relationship. So it's not going to make a huge difference. Whether I use LOM of 8 or I use LOM of 12, there is a slight deviation. And of course, if you are doing quantitative interpretation, which is the topic of my talk on Thursday, it will make a difference. But the difference is not so significant. This is the Duvernay section. And this is the zone of interest, 17 meters thick. Upper Duvernay zone here, cross plot of Mu-rho and lambda-rho. It doesn't, I picked up all these points here. It doesn't highlight that at all, because the resolution of your data is not good enough to resolve the 17 meters. I go with E-rho and the sigma, which I have boasted about. Well, E-rho works very well. Even that doesn't work here. Look, upper Duvernay, it is not highlighted at all. So what I do is I run this thin bed reflectivity inversion on my data. The P wave reflectivity I'm showing you. This is the enhancement I get. Now I correlate with the log control. This is the synthetic in blue. Red is the real data that you see there. And my zone of interest is here. Thin zone here. And after I do this, Mu-rho and lambda-rho I calculate, and now I pick up these zones. Notice I have something in the upper Duvernay zone, which I was missing in the earlier one. Similarly, if I have E-rho and sigma, again, I have something there, and I can populate that. Based on this, we were able to get some variation. The constrained data volume, 10 millisecond interval below the top Duvernay marker and 10 milliseconds below. So we were able to get these in the 20 millisecond zone. So the point I'm making is that this kind of variation, in the absence of proper bandwidth, you won't be able to see. But if you are able to do something like this, you will be able to see that kind of a thing. Going forward, delta log R is a function of impedance. Look at the scatter. As a function of lambda-rho, useless. This again is useless. Lambda-rho over lambda-rho plus mu-rho. You see, this is, well, it's not the best, but it's still better than the rest. So now, based on this, we were able to pick up this. This is the delta log R volume, 10 milliseconds interval below the Duvernay marker. And this is what we have from the previous one that I showed. Notice they are not very different. So this comes as a check, because this core data we were given after the fact. After we had done the exercise, we had delivered all the attributes, then they provided the core data. And the core data was over only 10 milliseconds zone. And you see there are very few points, I think 10 or 11 points at which we have the core samples. And so the red one is coming from the core samples, and the TOC from the core samples, and this delta log R is the inverted delta log R that I show you in blue. Notice this matching here. This one is slightly off, but the trend is there. And again, I say this will have a bearing on the quantitative interpretation you want to do in the lower zone. But then my point is that if you want to do this kind of analysis, you need more data, not only over 10, 11 samples. So it should be not only at one point, it should be at different wells, so that we can get a sort of an average feel for a spatial variation. But this is only at one point, because that's all the data we were given. And I'll just conclude this by giving you a feel or a flavor for what are the future directions where we are working on. You see, for simultaneous inversion, we use the near, the mid, and the far angle stacks. And then we we extract the wavelet from the three. And there's always a lowering of frequency as we go to the far offsets. This is not a good thing, because it lowers the overall resolution. So what we are doing is, we are trying to balance this on the near, mid, far for the same bandwidth as the near offset. And we are trying to balance the amplitude spectra, as you see here. And now look at the wavelets that we have, they are all similar. This leads to somewhat better results.
Sorry, when you adjust the FAR, is that all just looking at pre-stack data? You're trying to adjust it there, or are you just adjusting
we have the
the
angle
stack
stacks.
after?
We have the angle stacks.
Yeah.
Near bit far. So you are trying to bring the far also to the near bandwidth.
Yeah.
The middle also to the near bandwidth.
But are you doing that on the data before you stack it, or you're actually doing it on the stacks themselves and then trying?
It's a post-stack process.
It's a post-stack process.
So,
Okay.
yeah. So here I get the angle stacks, and then I balance this. And once I balance this, look at the amplitude variation. Because when you are increasing the frequency, your amplitudes are going to change somewhat. Means the level of the amplitudes will be different. But look at the variation. This variation and this variation, very similar. The trends are maintained. And so we know that we've been playing around with this for quite a few years now. So it works. And based on this, look at the P impedance volume using the conventional workflow. And after this, revised workflow. There is more detail on this now. And that is a shortcoming of the inversion process. I shouldn't say the inversion process, but the seismic data itself. Because we have lowering of frequency on the far offsets. Similarly, this is S impedance. Notice on the conventional, and this is the revised workflow. And then I have VP by VS, conventional, and this one. Notice there is a lot of difference between the two. Sorry, conventional and this. So, and one last bit here. When you are doing joint inversion, that means you are processing multi-component data. PS data again has a lowering of frequency because it is not the same frequency bandwidth as the PP data. Even when you bring it to the PP time after registration and all. So look at the bandwidth here of the PS data and look at the bandwidth. Again, we are not extending the bandwidth, still the same bandwidth, but we are trying to balance it a little better. So, sorry, this one goes here, but look at the section as such. Look at the detail here and after the balancing. This also makes a difference, this much. This is your the statistical wavelets extracted from PP and PS. The lower one is PS data, obviously. And this is what we do when we balance it. Look at the wavelets, similar. And now, look at this section. This is the segment of the VP by VS section that has been derived. And this is what you get now. Look at the continuity, the resolution. So, in conclusion, what have I said here? Shale resource characterization may not be a straightforward exercise. A workflow that may work in one area may not work in another. So you have to tailor make your workflows for individual projects. And the availability of all the relevant information, it helps in doing a more accurate job of characterization. And the more data you have, or you bring that data into your computation, into your project, the more it is going to help in your characterization. So with this, I thank you for your attention.